Hi, everybody. Hi, Armando. My name is Sofia, as it has been said, and I'm a cryptography researcher and implementer at Cloudflare. And I also lead the design of the version 4 of a protocol that's called the off-the-record messaging protocol. And I do implementation and design of cryptographic protocols of many things. And one of the things that I was wanting to talk today is a topic that I've seen posed as a question to many people. So I was wanting to introduce that. And with that, I'm going to share my screen. Hopefully it will work. Okay, here, share. Yes, and everybody should be seeing the presentation, hopefully. Yes? Yes,
yes, we do.
Okay, but without the Zoom chat, right? Without the Zoom interference? No Zoom? You don't see any Zoom, right?
Correct. I see the whole screen.
Okay, perfect. Okay, so welcome. And basically the name of the presentation, as it has been stated on the Meetup page, is the double-ratchet algorithm, its security and privacy properties. And as I said, the reason for this presentation was mainly that a lot of people have posed the question several times, what is the double-ratchet algorithm? Because it's very much widely used by most of the secure messaging protocols and applications that today exist, like Signal, like OTRN version 4, like Omimo, etc., etc. Okay. Yeah, so just to give a little bit of context as well. So one of the reasons why I also wanted to give this talk was not only to give an overview of what actually the algorithm is, but also to give a little bit of a context of why it got generated, why we needed to create this algorithm and so on. So for this, let's jump into a little bit of history. So what happened at the beginning? So in the beginning, we didn't really have a protocol that was and when I say the beginning, is the beginning of the internet, we didn't really have a protocol that tried to secure the communications that we were having, specifically the communications that we were having on instant chat. What we have were some efforts that at first were taken by the protocol that is now called TLS. At the beginning, there was the efforts to actually create this protocol, and at the time it was named SSL. So this was one of the first efforts that existed out there that tried to secure the communication that happened on the digital world, mainly the transactions and the network communications that we're having. But still, this was not an effort to actually secure the communications that we have over a chatting system or over email for that matter. The second protocol that actually tried to give secure communications and privacy properties out there was PGP, which stands for Pretty Good Privacy, and it's basically today used to encrypt emails or sometimes to encrypt certain types of files. I think it works better for certain types of files, but to others. But yeah, basically that was like the state of the art during the time of what you can actually use to secure your communications, either your email or the network communications that you were having. And because of that, three cryptographers came together by the name of Ian Goldberg, Nikita Borisov, and Eric Brewer, and they decided to analyze the security and privacy properties that these two protocols were given, the TLS protocol and the PGP protocol. And for this, they wrote a paper in 2009, which basically looked at these two protocols and said, okay, the security and privacy properties that these protocols are given us are these, but these are not enough. And the reason why they say that they were not enough is because they looked at the conversations that we have in the real world, and they say in the real world we have certain properties, privacy and security properties, that are not getting mimicked and that are not really having a counterpart in the digital communications that we have. Specifically, they look at two properties, which are the properties of deniability and the property of forward secrecy. And the reason why the protocols of PGP or TLS don't actually have these properties is, for example, that in PGP, you can sign messages, which creates an actual record, a proof of authorship that you indeed are the person who sent a message. And they say this doesn't mimic the conversations that we have in the real world, because in the real world, we can always deny having said anything in a conversation. For example, if I say to a friend, I really hate this X person, And this colleague of me, this friend of mine, later goes to this expert and said, hey, Sophie really hates you. I can always deny having said so. I can always say, like, yeah, I really didn't say so, unless I was recorded in some form. But it's usually in most of the countries that exist in the world, not on all of them, but in most of the countries that exist out there, it's illegal to record anyone without the permission of this person. So what they did is that they look at the real world conversations and they look at the protocols that existed out there and they say, okay, it's not enough because the properties that we have in the real world are not being sustained in the digital conversations that we have. And they looked at this and they say this is a problem because most of the times when people use the digital world, when they have chat conversations with someone over the digital world, they assume that the same properties hold, while in fact they don't hold. Okay, so they saw all of these problems. So that's why so they saw all of these problems and all of these properties, and they decided, hey, let's create now a protocol that indeed gives these properties that we see that they are lacking. And that's why they created the first version of this protocol that's called the off-the-record messaging protocol. And they put it out there since 2004. It has had 3 versions. Now it's also a 4th version coming. But yeah. Okay, and a little bit more of history around that is that, of course, we had this really beautiful protocol that is the off-the-record messaging protocol, but it sort of got obsolete because during that time, the off-the-record messaging protocol was not updated to the new communication model that existed out there. And that's why on the last 3 years, I think, or no, on the last years, there has been another protocol that is sort of the evolution of the record messaging protocol, which is the Signal protocol, that tried to take almost all the properties from OTR and create a modern protocol with its new properties. So for this, let's start with the properties, some of them that are already listed, but let's give a clear definition of what are them. So the first property that, of course, all of the secure messaging protocols try to give, and the properties that PGP does not have in the present, is, for example, the property of always secrecy. And what does this mean? It means that if you're trying to encrypt a message in a conversation, each message is going to be encrypted with a unique key, which means that any traffic that you send gets locked in the past. Like, for example, let's say that you send a message saying hello, then you send another message that says how are you, and then you send another message saying I'm Sophie. Each one of those 3 messages are going to be encrypted with a unique key, and if an attacker gets hold of that unique key that encrypted the I'm Sophie message, this attacker will not be able to decrypt any of the past messages, meaning he will not be able to decrypt the hi or the how are you message, because those messages would have been encrypted also with a unique key that is different from the one that the attacker got hold of. So this forward secret is basically that property that even though if an attacker gets hold of one key at the present, any past messages that were sent are going to be secure because they are encrypted with different keys. And here is sort of here on the slide, you see a sort of a more cryptographic definition of the properties. How is this achieved? So this is one of the properties that this protocol that I talked about, that is the off-the-record messaging protocol, tried to achieve. And the way that it achieved at that time is by the usage of this algorithm that is called the DiffieHellman key exchange. So how the DiffieHellman key exchange works basically is that you generate 2 keys, one private and one public. The public key, yes, you generate one private key and one public key, and the other party, the one that you were trying to communicate with, also generates 2 keys, which is a private key and a public key. And basically, when you want to encrypt a message, what you do is that by using the public key of the other participant, you exponentiate it or you multiply it to the secret key that you have, and you have a secret key, a shared secret key that you share with the other participant. And later you can use the shared secret to actually derive for the keys in able to be encrypt the messages that you're going to send. And this is all nice and beautiful. If you're going to implement it, go for it. It's really simple to implement. It's one of the simplest and most nice algorithms that we have out there. Unluckily, if quantum computers ever come to a reality, this is going to be broken, which is a shame because it's really beautiful. But what is the problem that that the signal developers, for example, found? If you're using something as the DiffieHellman algorithm, of course, any traffic that you sent in the past is going to be locked in the past, because every time that you're going to send a message, you're going to generate different keys. You're going to generate a private key and you generated a public key, and you will use them to encrypt your message. Of course, this is beautiful, but it means that it's a little bit computationally ineffective, because you will have to be generating every time that you want to send a message, you will have to be generating keys, which will take a time for the computer to actually do, which we don't want. And the other problem that exists out there, and that makes this not enough for the property that we want, is that of course this will handle in order messages, because you need to advertise always to the other person your public key. The messages have to arrive in a certain order, and in order because you will have to take the correct public key of the other participant. So a network that handles out of order messages will not be able to handle this, because you will always need to have an in-order network exchange. Of course, this can be easily solved if, for example, you force the network that you are putting your protocol on top of to always be in order, but it's not ideal, because the idea behind secure messaging protocols is that they work on top of whatever network exists out there. And if this network actually does package reordering or handles out of order messages, then your protocol has to do that as well. So the signal developers look at this and say, okay, this is not enough, very cool. We can base upon a new algorithm upon this, but it's not enough. Okay, and the second property that the signal developers wanted to give, that is sort of related to the first property that I talked about, the property of forward secrecy, is the second property that's called backward secrecy. What does backward secrecy mean? If forward secrecy was going to try to protect traffic that was sent in the past, forward secrecy is going to protect traffic that is sent in the future. So even if an attacker gets hold of one key that was used to encrypt a message, this attacker will not be able to derive new keys to decrypt future messages, because each message is encrypted with a different key. This is impossible to do that right now, the way that I describe it, and even the current protocols that exist out there, on MIMO or Signal or WAR, does not give backward secrecy in its full perfection. Rather, they give a variant of backward secrecy, which is called post-compromise security. What does post-compromise security mean? It means that during a time frame, your traffic might be able to be derived. The keys that were used to encrypt your traffic might be able to be derived, but then the channel will self-heal itself. So, for example, let's say that you send 3 messages. Hi, how are you, Sophie? Those messages, if the attacker gets hold of the hi, he will be able to derive the keys until I'm Sophie. But at that point, you will add new randomness and the channel will self-heal. So there's a time of compromise, as you see, until you add new randomness, you add different keys, and then it will self-heal again. So in conclusion, none of the protocols that exist out there actually give perfect backward secrecy, but they give post-compromise security. And here, as well as in the slide, this is the cryptographic definition of the property itself. Okay, so those are, from a security standpoint of view, those are the 2 properties that actually the Signal protocol wanted to give to its users. Now, a little bit of a note here, prior to introducing actually the double-ratchet algorithm itself, is that this algorithm always happens after an A key. And in a few slides, you will see why this is really important to define. But basically, I will define right now what an A key is. An A key is an authenticated key exchange, which is basically an algorithm as well that performs a series of the steps that will make you authenticate to the other party to say, indeed, yes, indeed, this is me talking in this conversation. And they will make you also derive the first shared secret. So one of the inputs that are needed to actually initialize a double-ratchet algorithm is that you first generate somehow, by using an A key or whatever you use, to generate a shared secret that is going to be the input to the double-ratchet algorithm itself. So, for example, in the case of Signal, they use as A key they use X3DH. In the case of MIMO, I think they only use 3DH. In the case of OLM, I think they also use 3DH. In the case of OTI in version 4, we use a different variant of an A key, which is called a deniable authenticated exchange. But well, this is one of the things that you should actually have to note, because one of the assumptions that I have seen when people write protocols or trying to implement the double-ratchet algorithm is that they assume that the double-ratchet algorithm is the whole thing, an AKE plus the double-ratchet algorithm itself, when it's not. The double-ratchet algorithm is just the process by which you are deriving new keys and sending and advertising these keys to the other participant to generate encryption keys to encrypt the different message that you're going to send. But it's not an algorithm to authenticate, nor an algorithm to generate the first shared secret. Okay, and as we know, the double-ratchet algorithm was designed by Trevor Perrin and Moxie Marlinspike, which are the creators of the Signal protocol and also of the Signal application itself. So basically how the double-ratchet algorithm works. You will have two participants, you will have Alice and you have Bob, or whatever you want to call them. And Alice, as I said, has to have a shared secret that was previously generated by the usage of another algorithm that would have generated this key. And she will also need to have the first public key of the other party that you're communicated with. So a requirement prior for the algorithm, as I say, is that somehow you generated a shared key that is shared between the two participants, and that somehow you were transmitted the public key of the other participant. And both will have the same. You will have a shared secret, yes, and it will have his own private key, which corresponds to the one that Alice has. Then what Alice will do is that she will generate new randomness. She will generate her own DiffieHellman keys. And from this, she will use, and for this, she will calculate a new shared secret from the public key both transmitted and from her newly generated private key. And from this, she will derive a lot of keys. Now, why is it called a double-ratchet algorithm? Because at this point, we are having the first ratchet, which is called the DiffieHellman ratchet, at the moment that Alice is generated the DiffieHellman key, the new randomness key. But at the point that she derives the encryption keys, this is called sort of the inside ratchet. So you have this ratchet and an outside ratchet over here. That's why it's called the double-ratchet algorithm. So at the point that she generated the Diffie-Hellman keys, from this Diffie-Hellman key, she will start deriving by using an algorithm that's called a key derivation function. She will derive a set of keys that will lead to actually generate the key that is going to be used to encrypt a message. So as you see, at this point, she calculates this sort of master key that is the Diffie-Hellman key. But then when she wants to send a message, she generates these derived keys from the master key, this one, and then she derives another one if she wants to send another message. But she is not generating any new master key at this point. When Bob receives the message, he does the same. He takes the public key from Alice, and then he uses his own private key to generate the master key, and then from there he derives the per message keys that are needed. If at some point Alice wants now, after receiving messages from Bob, she wants to send a new message, then she will derive new master keys, and from then she will derive the per ratchet keys. So what we see at this point is that the double ratchet algorithm works in a ping-pong way, which means that when Alice sends messages, she will derive only one master key, and from the master key she will derive per message keys. But at the point that she receives messages from Bob, she will derive a new master key. So how this works? Alice wants to send, for example, two messages. She wants to send hi, and she wants to say, I'm Alice. At the first point, she will say, okay, I'm going to derive a new master key. And then I'm going to derive from this master key, I'm going to derive a per message key. So I'm going to derive one per message key for hi, and I'm going to derive another per message key from how are you? And she derives these two message keys. If she wants to send more messages, she keeps deriving from the master key. Bob receives this, Bob derives the same master key, and then he derives the per message keys. The per message keys that needs to decrypt the messages. If at some point Bob wants to send the subsequent messages hi, and then I'm Bob, he will derive a new master key for himself, and then he will derive per message keys for each message that he wants to send. When Alice receives, he will derive a new master key if she wants to send new messages. So as you see, this is a ping pong, because only when you receive messages and you say, hey, I received messages from Bob and now I want to send messages, is that you derive these new master keys again. So it's a ping pong. You wait for the other to send you some messages and that you receive in order to derive new master keys. But if you never get messages from the other side and you never get any conversation from him, you will only derive one master key, and then from one master key you will derive per message keys forever. So yeah. Okay, and as I said, this is post-compromise in the sense of giving a time frame. Why? Because Alice only derives a master key per until she receives some messages from Bob. So for example, Alice sends hi as a one message, Alice's second message, how are you as a third message, and all of these messages are derived from a one master key. So that means that if an attacker gets hold of one of the per message keys, this attacker will be able to decrypt all of the subsequent keys until you receive a message from the other party and you derive a new message key, a new master key. So as you see, it has a time frame in which the algorithm can be compromised, but it's usually a short time frame until the other party answers to you. There was a really interesting paper 2 years ago by Arwin Coretti and Dodis that were the first to actually analyze the double-ratchet algorithm and in general the signal protocol, because one of the criticisms that the cryptography community got was that the signal protocol was widely used by many people in the community and many people worldwide without having actually a revision and actually cryptographers actually checking that indeed the algorithm was given the security properties that indeed it claimed to be given. So this was the first study that someone did to actually say, yes, indeed, the double-ratchet algorithm and the signal protocol are indeed given the security and privacy properties that they claim they are giving. And they say, yes, they are indeed giving those properties, so that's good. But what they also found out is that the double-ratchet algorithm has two other properties that were not considered at the beginning, but they were found by doing this study. And the properties, the first one is that you have immediate decryption, because once you receive a message, you are immediately able to decrypt. This is not true with other proposals of other secure messaging protocols and other algorithms, because in other algorithms, you have to wait for a time until you receive the correct key to be able to decrypt a message. And the second thing is that you have message loss resilience and the ability to actually handle out of order or lost messages. And this is really important because the double-ratchet algorithm is not as simple as I defined it, because actually when you're sending messages, you also send other things that you advertise. You advertise the number of messages that you have sent. You advertise the number of messages that you have sent per ratchet. And this allows you, for example, if one of your messages got lost, this allows you to derive intermediate keys. So when the message actually arrives, you have already stored a derived key, so you're able to decrypt this message. And that's also something good. That's the novelty of, in general, of the double-ratchet algorithm, that is able to decrypt intermediate keys of messages that are still waiting to arrive to you. So it's able to handle out of order and message loss resilience. As I said, it's important to know that, of course, the double-ratchet algorithm, as I said at the beginning, happens after an AKE. So if you want to use the double-ratchet algorithm in any protocol or in any application that you want to have, you have to have generated a shared secret and a public key for one of the parties. So that's always have to happen prior to the double-ratchet algorithm. The double-ratchet algorithm expects that as an algorithm. It's important to note that the keys are always advertised on sent messages, and this might be something bad if you want to implement in certain protocol in which you are always careful about a network adversary looking at messages and trying to gain information from them. Because the keys are advertised in each message, then it might leak some information about whatever is happening. So the double-ratchet algorithm also gives you an ability to encrypt the header if you want. And of course, as I say, there are many other values to keep track of. I just gave like the simple version of the double-ratchet algorithm, but there are many other values that you have to keep track of. Mainly the number of messages that you have sent, the number of messages that you have sent in a ratchet. Why these two values are important is because they're important to actually generate the intermediate keys in case that your messages get lost because the network dropped or because the network decided to do some out of order or decided to do a reordering that you were not aware of. as I said, the double-ratchet algorithm expects prior to it that shared secrets and authentication happens. So the double-ratchet algorithm is not going to give you authentication, and it's not going to give you deniability. The second point is really important because sometimes when people implement the double-ratchet algorithm in the protocols, they assume that it will give you the property of deniability. Deniability is actually achieved by the way that you transmit to the other party your long-term keys. So if the key, the algorithm prior to the double-ratchet algorithm is not deniable, then the double-ratchet algorithm is not going to give you deniability. So if you want to have deniability in the pure protocol, you have to take further steps, more than actually only having the double-ratchet algorithm. Now, the double-ratchet algorithm, because of the way it's written, will not diminish the deniability once you have it in your overall protocol, but will not give it per se. Okay. There's some things also to take into account if you want to implement the double-ratchet algorithm by itself. Of course, as I said, because the double-ratchet algorithm handles out of order and handles message loss resilience, drop packet, drop messages, etc., 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 there will be a list of awaiting to be used keys that you will have internally until the correct message arrives. It might never arrive. But what is the problem with this? If you have the list forever in your application stored somewhere, an adversary might want to get hold of that list and actually use that list of keys for something. For example, let's say that an adversary has been looking at your network and taking some messages so they don't reach you, and later manages to get hold of that stored keys list, then he will be able, this adversary will be able to decrypt those messages. So one of the recommendations that the signal developers, the signal researchers do is that you should expire these stored keys. They should only exist in your memory for a while. And you can actually define in your own protocol what this time is, but it should be long enough to handle the reach of drop messages, but small enough to not allow an adversary to attack you. Another important step is that this protocol needs a thing that's called secure deletion. Because of course you're handling lots of keys. I did a simplified version of the double-ratchet algorithm, but in memory you might have 1, 2, root, chain, 6 keys at some point, many more other keys, and all of these keys should be securely deleted. This is not a trivial task because adversaries can actually look at memory in many different ways and actually delete and actually get them. So it's actually always important if you're going to implement the double-ratchet algorithm that you have also in plans a way to securely delete the keys that are generated into your protocol. Now, there's a problem also in the double-ratchet algorithm that some people have found out, and it's the problem of what happens if both participants start the double-ratchet algorithm at the same time. So if you read the documentation of the double-ratchet algorithm on the Signal website, you will find that they have a definition of the algorithm only for when one of the parties starts the double-ratchet algorithm. But when both of the parties will start at the same time, there can be a little bit of a disorder that can happen in itself that will lead into problems. So you always will have to have a strategy to how to handle when both of them want to initialize the algorithm. The website and the protocol itself gives some recommendations, so you can always read them. And of course, something more important to note is that this does not protect against device compromise. So if someone gets hold of your device, they will be able to maybe see the keys that you're having, or maybe they will be able to inject some other keys that they want, so the other party, so they will be able to have a conversation with other parties. It's not perfect, as is all in cryptography. We are bounded by the hardware we are working, and if the hardware gets seized, then most of the properties that you have seen here will not hold anymore, because they only protect to a certain point. But if an adversary managed to get hold of whatever hardware you're using, then they will be able to do lots of things. Okay,
Sophia,
and this is also...
Before you move on, Lark had a question in
sorry,
chat, which was
the chat.
That's fine. He was asking, is there a recommended duration for how long to keep the keys?
I think the recommendation on the protocol itself was like a week, but that's all. But it depends on your protocol itself, what you want to give. Sometimes it might be hours. If, for example, you have a really you're using your protocol for people who have a really dangerous threat model, then probably expire them as soon as possible, or don't store them at all if you wish. Okay.
Thank you.
Okay, so why is this so used? Because one of the things that happened also is that I guess over the last 3 years, the Signal protocol has really taken off, and a lot of people are actually looking at implementing the double-ratchet algorithm itself. So why it's used? Because it gives you really nice properties, but by being not a really difficult algorithm to implement. So once you really get hold of how it understands, it's really easy to implement, because the only primitives that you will be deriving is some way to generate DiffieHellman keys by using some elliptic curve, or you can use DiffieHellman itself. And for the key generation, you can use HMAC, or you can use any or SHA-3 of any of the SHA-3 family if you want. You can also use. So it's actually really easy to actually implement, and that is one of the reasons why people are using it. Plus the security properties that it has been giving. Okay, and the last thing that I always talk is that, of course, with protocols, sometimes you read all of these properties, but it's also important to know that sometimes even if a protocol gives certain property, it doesn't mean that it gives the strongest version of this property, or the property in fullness itself. As we saw in a previous slide, for example, the Signal protocol or the double-ratchet algorithm itself, for example, doesn't give the perfect version of backward secrecy, but a flavor of it, which was the post-compromise security. So in terms of, for example, forward secrecy, the Signal and double-ratchet has a weak version of forward secrecy, because at some point, only one of the parties that initialize the algorithm itself will have actually the strongest notions of forward secrecy, and therefore it's a weak version of it. And you can see here the same reproduces, for example, for MIMO, because MIMO uses the double-ratchet algorithm the same way that Signal uses it. They use a different key. I think they still use the triple DiffieHellman. I'm not sure. Maybe they use the extended triple DiffieHellman. I will have to check. But yeah, something that still needs to be researched, and maybe this is something, there's some cryptographic researchers out here that needs to still be researched, is actually what kind of level of post-compromise secrecy is being given by the double-ratchet algorithm itself. I also put here all the properties of, for example, deniability. This talks not about deniability, but in general, the flavors that the Signal protocol in its fullness, not only the double-ratchet algorithm, are not really that deniable, but we can talk that on another occasion. Okay, and with that, that's all that I wanted to talk about. So if you have any questions, go for it. So thank you. Okay, I'm going to stop sharing my screen. Good.
That was amazing. Thank you so much, Sophia. Anyone has any questions, please feel free to either post in chat or unmute yourself and go ahead and ask.
I'll break the ice. So thank you, Sophia. That was really useful. You mentioned, thank you for describing the double-ratchet algorithm. So it's the first time I've ever really heard somebody describe that. I'm wondering if you misspoke at one point. You said that if an attacker compromises a message key, that they could derive other message keys that are part of the same master key. Was that true? Or did you mean to say if the attacker compromises the master key, then they can derive all subsequent message keys?
Okay, so if they get hold of a master, I call them master. It's not really master, but that's the way I call them.
It's a per
key,
ping pong, or
yes,
per volley.
per DiffieHellman ratchet key.
Yeah.
And they will be able to derive all the keys on that DiffieHellman ratchet. If they manage to get hold of one of the message keys, they will be able to derive subsequent keys as well. They will be able, because it's a key derivation function that basically works like this. The key derivation function usually needs the previous message key, and they will generate the future message key. So they will be able for a while until the new DiffieHellman per DiffieHellman key will be generated.
Oh, okay, interesting. And that's why you can use SHA-1. Okay, so then the way that it got it. So just to make sure that I understand the other thing, and then I'll shut up and yield the floor. So, so the way then that you can deal with out-of-order messages is it's opportunistically or proactively generating a set of future keys as well, right? And okay, so it can't look backwards, right? Because that's the post-compromise thing that you were talking about. It can't it can't generate previous keys unless you're going to search the entire hash space. But for every future one, then it can actually get those as well. Cool.
Yes. And what happens is that usually, for example, you send a message and you will advertise the DiffieHellman key, the master key, and you will also advertise how many messages until that point have been generated. So it will say, like, for example, 3 to this point. So when the other participant gets it, it will say 3, but I only received 2. So that will mean that one message is still in arriving. So I will generate that intermediate message that I need for that moment. That's basically how to do it. What they send is two parameters. They send the current number and the current number of how many messages can be. So they say, like, this message is the 3rd one, and until this point we have had 3 messages. So that comes and arrives, and for the other party we say, okay, until this point they say that it has been 3, but I only have 1, and this says that it's the 3rd message. So I need to generate the key for the 2nd one that has been arrived, and you store it. Okay. Potentially, you will also be able to generate the future keys of the messages if you want, until new randomness is added, until a new DiffieHellman key will be generated.
Cool.
Anyone else have a question?
How about the randomness? How do you provide it? Is it one of the DiffieHellman parameters?
When you generated a private key, you will have to generate it by some sort of randomness. So every time that you generate a DiffieHellman key, you will have a private key that will be generated from randomness, and then you will have a generator. So basically in DiffieHellman, you will have a parameter that is called G, which is the generator. And to this G, you will exponentiate this G to the randomness, to the private key, and from there you will generate your public key if you're using DiffieHellman. If you're using something like elliptic curve cryptography, what you will have is the same, but instead of doing an exponentiation, what you will do is another operation that's called a scalar multiplication. Thanks. But it's basically the same. The principle is the same for that matter. LV4, you signal, you store. What's LV4? I don't know what that means.
Yeah, I don't know what LNB4 means.
It's IN before. Like, you know somebody's going to say something and you stick it in before. It's.
Oh, I see. Okay. I have a question. So to deal with missing messages, we have to maintain some state, right? The intermediate keys, and remember them. In your experience, when people implement this, how do they handle, like, how much of missing messages should I handle, right? Like, should I wait for 10? Should I wait for 20? What do people do in that situation?
So for example, in the OTA version 4 protocol, we recommend 1 week that you can store, and then they get deleted. But it depends on the network that you're using. Most of the times the network will not do out of order, because most of the networks that exist out there will eventually do an order. Even if they arrive out of order, I think that's TCP's 101. they will order back the packages or how they were sent. But of course, there exists other networks that will do some kind of out of order delivery. The other one, OCP, for example, will do that. OTP, yes. Will do.
There's a question in chat, which is, do you know if electron vulnerability remote code execution enables an attacker to exploit the private key?
I don't know what the electron vulnerability remote code execution is.
I think they're talking about in the desktop version of the Signal app. Sorry, okay. I don't want to put words in your mouth, but is that correct?
To me?
Oh no, for the person who asked via chat.
Okay, AY. Well, AY continues to.
Okay, I know a tiny bit about that. So because basically it's implemented the same way that WhatsApp Web is. So so Signal desktop just uses the keys that are in the phone, in the mobile device, to encrypt the messages, and it uses secure key storage. So basically all it is basically like a remote keyboard and video display for what's actually happening in the phone. So so yes, if somebody was able to compromise the desktop app, they might be able to send a message, or pull back existing messages that have already been decrypted, but they wouldn't have access to the underlying key material itself.
Yeah, I think so as well.
Yeah.
Yeah,
Sorry. So yeah. So AY's got it. Cool. AY had another question. So sorry. Go ahead, Sophia.
So I think the same. So to have actually access to the keys, they usually are not sent over the network, even though this is sort of different from group messaging. But let's say in a one-on-one conversation, they will not be sent actually. The private keys are not sent over the network. So it's really difficult to actually just get hold of them unless someone seizes your device, which can happen in some things. Okay.
There was another question.
Another one.
Oh yeah.
Okay, you go.
I think you said.
Okay. What are some resources or books you recommend for people interested to study the applied cryptography? The Applied Cryptography by Bruce Schneider, that's a great book. He also have a blog, which is also great. There's also, if you want some actual courses, there's the cryptography, I think it's called Cryptography 1 by Dan Bonnet that you can take on Coursera. Supposedly there's a second part of that course that will come someday, but you can also have it. There's on the same Coursera, I think there's also a nice, I think it's Gus Kramer, the one who gives it, but there's another course that you can take from cryptography. That's also pretty good. Yeah.
I have found there's a German professor, Christoph Barr. His book is really good as well for beginners. I forget what the book is.
He also has the set of his talks in YouTube if you want to watch him.
Right.
Yes.
I think his book is called Understanding Cryptography. Understanding Cryptography by Christoph Barr. I think that's a really good book. All right. Any other questions?
By Nigel Smart, that was really good, because I really like the way Nigel Smart teaches. But I don't remember the name.
Cryptography Made Simple.
Yes, I love him.
I was gonna say it's it's a great book. I think for the beginners especially, it's much more compact than many other books. So to get started, it's an amazing book.
Yeah.
I'll go with one more question if nobody minds. Sorry, I always have a lot of questions. So what is the rationale in doing a new DiffieHellman on each alternating handoff of the conversation? It seems like it would make sense that you would just kind of say, okay, we have 10 or 100 messages, even without that sort of ping pong message, like let's go ahead and generate a new DH anyway. So can you talk a little bit about what that rationale is?
Yeah, so at the beginning, there were some proposals actually from them at the beginning of the writing of the double-ratchet algorithm. For example, let's use a time frame. Let's say that if after like 5 seconds, we will generate new keys. Of course, that's not great because you will have to synchronize time between each other and might not be able to do that. In case of the number of messages, I think it was considered, but it was thought that it was a little bit more efficient and also more in line of what the OTR protocol was doing at the beginning, to actually wait for the sort of this advertisement from the other party to actually derive new DiffieHellman keys. You potentially can do, let's say that you indeed receive 10 messages, but let's say, for example, that the 10th message itself never arrives to the other party to be able to decrypt the new DiffieHellman keys, then you might run into a problem. Yeah. For example, you will have to say, okay, let's say that it's every 10 messages that I sent and 10 messages that you receive. But if the 10th message never arrives, then the other party actually sort of derived the new keys, but the other party didn't. Of course, this will be able to be handled if way out of order, because you will potentially have to stop, but you will have to wait until the 11th message arrives to realize that indeed you needed to have the 10th message there and derive new randomness.
Is the DiffieHellman key exchange handled like as like a little metadata attached to the message, the Pong message?
Yes. So every time that, for example, that you derive a new key, you will have to advertise to the other person your public key by sending like this metadata attached to your message. So you send your encrypted message concatenated with, for example, the current number of the message you're sending, plus the current messages that you sent in this ratchet, and attach also your public key that you generated. So at the time that the other party receives, they see, oh, okay, I have my private key, and I'm going to take this new advertised public key, and I'm going to generate a shared key so I can derive more keys.
Okay, cool. Yeah, that's pretty elegant. Okay, cool, thank you.
Okay, sorry, I've done question. Wait, okay. There was a pre-shared key in the beginning. How should that be shared off the channel? Okay, so how that is shared is that it's actually not shared. You will be able to generate it by doing a DiffieHellman key exchange. So basically what you do is that you generate your private key, and from that private key, you generate your public key. You send to the other party your public key. The other party generates its own private key and its own public key, takes the other public key of the other participant and exponentiate it to your own public key. That's your shared secret. And you do the same from the other party. And you generate the same shared secret, even though you didn't transmit it specifically, the shared secret, but you generate at the same time. That's the magic of DiffieHellman. Yeah. But this has to happen in an algorithm that will happen prior to the double ratchet. You can use, potentially you can use classic DiffieHellman, but usually what the signal uses is a standard triple DiffieHellman, because it makes them authenticate at the same time of generating the shared secret. You can use something as a deck in the flavor of XCDH or DexDet, which make the two parties to be authenticated in a deniable way also. So it depends what kind of properties you also want to that algorithm. If you only want to generate a shared secret, you can use classic DiffieHellman.
Any other questions? Okay, if there are no questions, I'm going to stop recording.